edición del seminario. Voy a cambiar en inglés. It's a big pleasure for me to introduce you Professor Antoine Luhan. He's a professor in the University of Sao Paulo. And for me, it's a big pleasure because we met with Antoine a long time ago in Graz, while we were both postdoctoral researchers there. It's very nice to see you again, Antoine. Thank you for accepting our invitation. It was a pity that you couldn't come to Quito last year. Antoine was supposed to be part of the IFIP, but well, IFIP probably we will have you this year, fortunately. And anyways, it's very nice to have you here in this virtual version of our seminar. And Antoine is an expert in shape optimization, and this is what he's going to share with us today. So Antoine, the audience is yours.
Thank you. Thanks a lot, Sergio. And so it's 1 hour. I can talk 1 hour or 50 minutes, or is it?
40 minutes is perfect, yes.
Yeah. So yeah, I was really looking forward to come to the IFIP in Quito and discover Quito. I was really disappointed but I hope it's going to be maintained. It's maintained for next September, right? So
yes.
Let's see. Let's hope it can work. And we were preparing a quite large mini symposium, many people. So it's really, but anyway, let's hope for the best. So many thanks for the invitation. You can see I'm in my son's room. This is my new office. So maybe you like the paintings on the wall.
Decoration.
This is my new office now. Okay, so I want to talk about shape optimization and application to inverse problems. I work a lot on these two topics, and so I'm going to show some results that I did with some colleagues. There's Yuri Albuquerque, who is my PhD student here in São Paulo. There's Kevin Sturm, who is now in Vienna. And there's also Erwin Yusept, who is in Germany, in Duisburg-Essen. Okay, so first I'm going to do a quick explanation about inverse problem. Maybe, I don't know if the people in this seminario, they are used to inverse problems or not. So I think it's good to recall some basic ideas here. So a direct problem, what we call direct problem, is usually, you can summarize it like this. You have some initial conditions and you want to find the evolution of a physical system. So typically is like solving a PDE. Okay, this would be a direct problem. And the inverse problem is you have some measurements which correspond to the final state of a physical system, and you try to find, in a way, the initial conditions. So you can already see, of course, it's very summarized, but after that, I'm going to show more details about inverse problems. But you can see that these inverse problems, there's a problem about the amount of information that you have. It's not always possible to find the initial condition if you just have a few measurements of the final states. So there's a very important concept which is at the basis, the foundation of the concept of inverse problem is the concept of well-posedness of a problem. So you have three conditions for well-posedness. The first one is existence of a solution. The second is uniqueness of a solution, and then stability of the reconstruction. And we say that the problem is ill-posed if one of these conditions is not satisfied, in which case you need some regularization. And so many important inverse problems, there are many applications to inverse problems, like in tomography, geology, etc. And usually these problems, they are ill-posed. So there's a whole theory of inverse problems on how to do the regularization to obtain a good reconstruction. So in this talk, I'd like to show some results about two types of problems. The first one is electrical impedance tomography, which is a very famous inverse problem in mathematics. And then I will finish quickly with some a problem with seismic inversion. So EIT for electrical impedance tomography, it's an ill-posed problem. So you can see it like this. You have a domain D, which is, for instance, this square here. And you apply some electric currents on the boundary. I will call the electric currents G. And you measure some voltages H on the boundary. Or you can do the converse. You can apply voltages and measure currents. But here I'm going to show it like this. And you want to find the conductivity sigma, which matches the measurement H. So your data is the applied electric currents and the measurements of the voltages. And you try to find the conductivity so that the measurements of your model, they match the applied, the measurements that you have, the real data that you have as the measurements. So in this example, what I call the ground truth is the true solution, if you want. So when we do this numerical test, we assume that we know the solution to see if the algorithm works. So, and usually we call this the ground truth. That means we know what is the solution, but this allows to measure the efficiency of the algorithms. And this is an example of reconstruction. So I'm going to show you afterwards some numerical results. So the black lines, they would be the exact solution, and the red one would be the reconstruction. So you can see it's difficult to have an exact reconstruction for this type of problems because you don't have enough data. Okay. So applications, there's a lot of applications for EIT. So the advantages of the EIT is that it's low cost, it's not non-invasive, which means you don't need some surgery or some really heavy medical procedure. There's no radiation if you compare to something like computerized tomography or X-ray, for instance. It's portable. You can build some device which is easy to move around. But this disadvantages is that it has a poor signal to noise ratio and poor spatial resolution. So it's not a very precise technique for imaging, for medical imaging. So, I mean, it's a trade-off between these aspects, and but still you can use it in practice in medical imaging, for instance, for lung imaging, to monitor patients undergoing mechanical ventilation. And here we have at the USP, there's a group from Professor Lima, who he really builds these devices and he uses them for monitoring patients for mechanical ventilation. So it's really used in practice, and you can make some small device that you can take in an ambulance, for instance. So it's quite nice to make a quick diagnostic, and then you can have a better imaging at the hospital. So there's other application like breast imaging, and also, so this is for medical imaging. Then you have application in geophysics. Usually it's called ERT because they measure the resistivity, but it's very similar to EIT. So you can use to map groundwater, for mineral prospecting, archaeology, and you have application in civil engineering to detect some cracks and voids. So there's a lot of interesting applications. So now the mathematical models. There's several models that have been studied in the literature, because the very nice thing about the EIT is that you really have the whole spectrum between really theoretical mathematics and engineering. So you can really study a very theoretical problem, and it's very interesting from the mathematical point of view. And usually this more theoretical mathematics point of view is corresponds to the continuum model. In the continuum model, it's a simplified model, but for which you can really prove some very sophisticated mathematical results. So the idea is that you apply currents and you make measurements on the entire boundary, which is really a simplification of the real situation. But you can prove, the point is that you can prove some interesting results like uniqueness of reconstruction, this kind of stuff. Then a more recent study, an extension of this continuum model is when you have only partial measurements. Instead of having G and H on all of the boundary, you only have them on a smaller part, on a small part of the boundary, and you want to know if you can still have a unique reconstruction, for instance. And then there's some more realistic model like the electrode model, where you really model the fact that what you have in these pictures, you have some small patches, and on each patch you have electrodes. So the mathematical modeling for the equation is more complicated, but it's more realistic with respect to real data. And a model that there's some other models. I'm not going to talk about all the different models, but the model that we study in this work that I'm going to show is called the point electrode model. So the idea is to replace small electrodes by point electrodes, which are modeled by delta distributions. So there's some recent work on this, and I will show that this leads to some interesting mathematics because of the delta distributions. So we studied the particular case of sharp interface models. So this is the shape optimization part, where we're just going to optimize with respect to the geometrical shape. So the idea is the following. You have some piecewise constant conductivity, sigma omega. So it's equal to sigma 1 in a domain omega and sigma 0 outside of this domain omega. So it corresponds to this picture, okay? For instance, you have these two ellipses, and inside the interior of these two ellipses is a domain omega with the conductivity sigma 1. And outside of omega, you have the conductivity sigma z. So sigma 0 and sigma 1, they are constants, but they could also be some smooth function. In this case, it would be like a piecewise smooth reconstruction. But in this work, we look at the piecewise constant case. So the goal then of the inverse problem is to reconstruct the interface d omega. Okay, so you can either assume that you know the values of sigma 0, sigma 1, or the values of sigma 0 and sigma 1 can be also part of the reconstruction process. Okay. Then we are going to consider the case of partial measurements also. So that means we're going to apply currents and do measurements on the part gamma minus gamma 0. So gamma 0 in this work is like a grounded region, is a region where you have Dirichlet condition. So here I'm giving more details on the mathematical model now. So we have currents applied on a subset of the boundary, okay? So the support of G is the applied currents, is included in gamma minus gamma 0. So it's the red region. This is gamma minus gamma 0. That's where you apply the currents. Gamma 0 is a subset of gamma, and U is the solution to a mixed boundary value problem. So normally in EIT, the source F is equal to 0, but we just consider the slightly more general problem just to compute the shape derivative in a more general context. But in practice, we just have F is equal to 0. And then the G really corresponds to the applied currents. So here the H1 gamma, the gamma basically just means that you have a Dirichlet condition on gamma. Because H1 gamma, you see this C infinity gamma is function V which are zero on the gamma zero basically. And you have partial measurements on the subset gamma H of this. So you have some partial measurements on a subset of this red region, okay? So now I'm going to show you the optimization approach that we use for to solve the inverse prime. And to solve the inverse prime, you can use many different approaches, and the optimization approach is one possibility. So the idea first is that we don't have only one current, but we have a set of currents, because inverse prime is about maximizing the amount of information that you have to find the best reconstruction possible. So in general, in practice, you can apply many currents to get more information. And for each applied current, you get a corresponding measurement HI on the boundary gamma H. And so this GI and HI, they are associated with the true conductivity sigma star, or which is called usually the ground truth in inverse problem. Okay, so this is the truth, the exact solution. So we consider a piecewise constant conductivity. This one I already explained. And I will call UI the potential which corresponds to GI and the conductivity sigma omega. So UI is our model. Okay. So I will have a trial conductivity sigma during the optimization, and I will use the GI because I know the current which is applied. And the potential UI will correspond to this GI and to the conductivity sigma. So the goal is that our sigma omega converges towards the sigma star, okay, during the optimization. So now the Eit problem, then you can write it in this way. You have a set of currents and measurement GI and HI, and you want to find the shape omega such that UI is approximately equal to the measurements HI on the boundary where you do the measurements. So here it's not an equality, it's just approximately equal, because in practice you have noise in the data. So it's not possible to match exactly the measurements, but you try to get as close as possible. And we assume that, so the particularity of this work is that the gamma H is going to be a set of points, okay, on the boundary. And because often this gamma H is just some continuous one-dimensional set, but in this case, in this work, we only consider a set of points. And the optimization approach is to minimize the distance between your model UI at the point xk. Xk is a point on the set of measurements, and the HI at the point xk. So the HI is our real data, if you want. And so you want to find the omega such that your model UI coincides with the measurements HI. And we use a least square approach, so you have the square here. And so there are two sums. There's one sum for the points where you do the measurements, and the sum over I is the sum over the applied currents, okay? So if you do some continuous measurements, then instead of a sum over k, you would have an integral, typically. Okay, so if you are familiar with this kind of analysis, you will quickly notice that in fact, I couldn't do this really, this UI of xk, because my UI is only in H1, right? So it's not defined at the point xk. So this was just a formal presentation. So how can we solve this mathematically? Because ui of xk is not well defined because my u is only in principle in H1. And it's the usual mathematical framework for EIT is to consider the H1 space, okay? So if you are familiar with this kind of spaces, you know that in 2 dimension, the H1 is almost continuous function. It's called, I think, it's quasi-continuous functions. So you just need a little bit more regularity to have a U well defined at xk. So the idea is that instead of considering H1 space, we're going to consider W1 P space with P strictly greater than 2. So basically the P is going to be like a 2 plus epsilon. Okay, it's just very close to 2, but a little bit more regular than 2. Because the H1 is like W1, 2. So here you want W1, 2 plus epsilon space. And so well, the W1 gamma P is defined in a similar way as the H1 gamma, is the closure of the space in the W1 P norm. And the dual W minus 1 is just the dual of the space P prime, where you have the relation here between the P and the P prime, and they are conjugate. So if when the P is greater than 2, then the P prime is smaller than 2. So if the P is a 2 plus epsilon, then the P prime is like a 2 minus epsilon. I mean, it's not going to be the same epsilon, but you see what I mean. And then you define the equation for the potential in the same way. It's a mixed boundary value problem, but now the test function, they are in this W1P prime space, and the solution is in W1P. Okay, so you have this duality between the test function and the solution. So why is it interesting to do it like this? Is because then we can use the W1P estimates of Gröger, which it's a theory which is well known in PD constraint optimization, in optimal control. So, but in shape optimization, it was not used, and Kevin Sturm started to work on this recently, and then we did this for the EIT also. So the idea is that I'm going to explain afterward, but to compute the derivative with respect to the shape, we had to extend a method which is called average adjoint method to the case of Banach spaces, because usually it's used for Hilbert spaces like H1, but here we work with the Banach spaces W1P. So the idea was to extend this theory to Banach spaces. And this allows us to consider shape functional, which involves point evaluation. So it can be useful for many applications. Okay, so now I'm going to explain how to compute the shape derivative, because if I show you again this, my cost functional depends on the shape omega, and the omega is the shape where you have the conductivity sigma 1. So you try to reconstruct this omega. So the question is, to do the optimization, we want to compute the derivative to get a descent direction for an algorithm. So how do we compute the derivative with respect to omega? So the idea is to do some deformation using a diffeomorphism, which I call this phi, capital Phi index T. So this gives you a family of deformed shape omega T, which is you have a reference shape, which is the omega, and the phi T of omega is a perturbation of omega T. So like in this picture, you have the omega, you transform it with phi T, and it gives you this omega T. And phi T is a diffeomorphism, so you can go back to the shape omega with the inverse. And then the shape derivative is just the derivative with respect to this artificial time t. Okay, and you can see this t like a time for the perturbation. It depends, the shape derivative, okay, in fact, it's called Eulerian semi-derivative. I will explain in the next slides what is the shape derivative. And it depends on the v, which is the velocity, which is basically the derivative of the transformation at t equal to 0. And a simple example is this perturbation of identity, phi t equal to 1, identity, the identity transformation, plus tv, okay? But you can also define more sophisticated transformation using, for instance, the solution of EDO, okay? But basically this perturbation of identity, it gives you the main idea for this kind of transformation. So the shape derivative, we say that J, the cost functional, is shape differentiable at a shape omega. If this Eulerian semi-derivative, this one, if the limit exists for all the v in this space, and the function, the Eulerian semi-derivative is linear and continuous with respect to v, okay? And in this case, we call dj omega of v the shape derivative. So basically, this just means that to get a shape derivative, you just need basically linearity with respect to v and continuity. Because sometimes you can compute this Eulerian semi-derivative, but it's not linear with respect to v, for instance. This can happen. So then you have an important structure result from Zolesio, or sometimes called Adamar-Zolesio, because Adamar was the first to discover this kind of structure. So basically, if you have certain regularity assumptions on the shape omega and on the shape derivative, then you can show that the shape derivative has this structure. So which means basically that it only depends on the values of v on the boundary and only in the normal direction. Okay, so these are the two important aspects of the structure theorem. Basically, it says that the first order derivative does not depend on the tangential perturbation on the shape, because the tangential perturbation of the shape, they almost don't change the shape. At the first order, it's 0. At the second order, it has a contribution, but at first order, it's 0. And the v, only the boundary perturbation matter, because if you have some perturbation inside the domain, it doesn't change the shape globally. That's the idea of this result. So it's quite intuitive. But we'll see that this is actually quite important for the application, this kind of structure. So what is the main issue with this structure theorem, which is a very fundamental result for shape optimization, is that it requires at least C1 regularity for the domain. If you look at the hypothesis, you need d omega of class ck plus 1 with k positive. So that means at least C1. So that means this kind of structure, in fact, is for domains which are at least C1. And you can, in fact, show the structure somehow for less regular domains like polygon or Lipschitz domains, but it's very advanced result. I cannot really talk about this here. But the problem with this structure theorem is that the domains like polygons and Lipschitz domains, they are excluded. So the interesting question from the mathematical point of view is, can we generalize this kind of structure theorem, or what happens when you have less regularity of the domain than C1? When you have, in particular for the numerical application, polygons are very important, right? Because when you discretize, you usually work with polygons. And it turns out that instead of using the structure of the shape derivative, which is basically a boundary integral, you can keep the shape derivative as a domain integral, and this has a lot of interesting application. In this case, we call this the distributed shape derivative. There's many names: domain expression, volumetric expression, or weak form. I like the name weak form because there's an analogy with the weak and the strong form of PDEs. I will show later more explanation. And this notion of distributed shape derivative, there was many developments in the last five years, let's say. It started in 2010 with the paper of Berggren, and in the last 5 years there was many interesting developments for numerical applications. So let me show you with a more concrete example how it works. So let's say you have omega, a domain, a subdomain of D, and the boundary expression of the shape derivative usually has this form. Okay, it's an integral on the boundary of omega. There's this function g which depends on the problem, and you have this v scalar n term. So this really corresponds to the structure theorem. If you look, this is really this form. Here the g of v scalar n is this integral of the g would be this function which associates the integral. And the distributed expression takes this form. So it's an integral over omega of S1 scalar dv plus S0 scalar v. So here S1 is like a matrix. It's a second order tensor. So it's like a matrix valued function. And S0 is a vector. Okay, it's a vector valued function. And you can see the difference between these two is that here you have one derivative over v. Here you don't have derivative over v, but here you have the domain integral. And here you have the boundary of the domain. Okay. So there's an interesting analogy with PDEs, the weak and the strong form of the PDEs, because you can imagine the v like a test function. When you consider the weak form of the Laplacian, for instance, you're going to put one derivative on the test function. So here is the same. You put one derivative on the test function v. And in the strong form, you don't have derivative on v. But on the other hand, the d of omega is like the derivative of the domain, if you want. So you get one derivative on the domain, but here you don't have the derivative on the domain. So it's the same as there's a kind of trade-off between the regularity of the domain and the regularity of v. In the distributed expression, you need more regularity of v, but less regularity of the domain. Okay? And here the trade-off, you need less regularity of v and more regularity of the domain. So this form of the distributed expression is known since the beginning of this discipline of shape optimization, but was not so much explored. The boundary expression was much more explored until now, because it's like a canonical form of the shape derivative. But it turns out that the distributed expression has a lot of nice applications too, and we're working a lot on this in the last 3 years. So when the domain is smooth, in fact, these two expressions, they just coincide. When the boundary expression exists, you automatically have the distributed expression which exists also. The relation between the two is just the divergence theorem, basically. In this case, I just write this exponent surf for surface and vol for volume, and in this case, they are equal. But the interesting part about the distributed expression is that it's valid for domains which have a low regularity, like open domains, Lipschitz domain, or piecewise smooth domains like polygons. And from the numerical point of view, there was many paper published recently where they analyzed the difference when you use these two formulas with finite elements. And it's always, these papers, they always show that the distributed expression, they yield a better approximation. In the convergence rate, usually the exponent is higher for the distributed expression. So it's quite interesting for numerical application. And but until now, it's mostly the boundary expression that was used in the numerical algorithm. So it's really an improvement. Okay, so now I'm going to show this this theorem with a lot of notation. So there's a lot of technical stuff in this page, but I'm going to just talk about the most important aspect of these results. So this result is the main result of the paper we have on EIT with pointwise measurements, with point measurements. And you can recognize, we computed this distributed shape derivatives, okay? So you have this S1 and this S0 for the shape derivative. So this is for EIT. This is the derivative of the cost function for EIT. And this, this S1, it has this form. It depends on the gradient of the potential, the gradient of the adjoint P. And P is the solution of this equation. So it corresponds to this expression. You have this S1 dV and S0V. Here it's a bit more general because the S0V is a distribution. In this case, S0V is a function, but here is a bit more general because it's a distribution. Because the S0V, you have some Dirac mass here. And when you apply it to V, it gives you a V of xk. So, but I highlighted with colors the important aspects of this result. The first important aspect is that omega is only open, okay? So it's really, you only need a very low regularity of omega to get these results. This is the nice part. And the other interesting aspect is that the P, the adjoint, has less regularity than H1. It's only W1 Q prime, where the Q prime is smaller than 2. And so it's because you have the duality between the state and the adjoint state. The state is W1Q, with Q larger than 2, and the adjoint is W1Q prime, with Q prime smaller than 2, okay? It's because on the right-hand side, you have the derivative of the cost function, and it's a pointwise evaluation, this cost function. So it's like you have a Dirac mass on the right-hand side. So your test function, they have to be more regular than each one, and the P is less regular because of this. Okay, so this is the nice, the really nice result about using this result from Gröger is that when you write the entire optimization with these Banach spaces instead of H1, then you get this duality between the state and the adjoint, and the regularity of this function just results naturally from this framework, okay? Well, so this is not so important. It's just to explain that there's a relation between the S1 and the S0. It's like the divergence of S1 is equal to S0, something like this. But let me show you the more important result here for the boundary expression. So this, what I computed in this theorem is the distributed shape derivative, okay? It's an integral on the domain D. It's not on omega because it's a transmission prime. So it's like integral on D, in fact, is like an integral on omega and an integral on the complementary of omega. So when omega is a polygonal set, then we can write the shape derivative using this boundary expression. So you get an integral on d omega of the jump of S1 across the interface d omega applied to the normal vector scalar v. And this result is a immediate consequence of this expression, because there's some theorems which tells you that one, if you have enough regularity of the domain, you can just compute directly this distributed expression. So, but here you need only omega open. And when you do this, then omega is polygonal. So you need more regularity on the omega. And if omega is even more regular, is C1, then you can get this expression. Okay. So there's a little difference with this expression here, because here you have V scalar n. Here you only have V, which means you can have maybe some tangential components in the V. But here the tangential component of V becomes useless. Okay. You can see that this formula is not so practical for implementation, because if you write what is exactly this S1 plus minus S1 minus, is the jump of these quantities, is the jump across the interface of the sigma dnu dnp. Okay, so from a numerical point of view, computing this jump is really is a bit annoying, because I mean it's not so easy. You have to be careful when you compute this kind of jump across the interface. Okay, depends if you use finite difference or if you use finite elements, but it's not so, depending on the on which kind of method you're using, is not so trivial. Compared to this expression is much easier to implement, because it's just volumetric, right? And in fact, this formula I can obtain immediately if omega is C1, but if you work a bit more, you can prove that it's actually valid also on polygons. There's a recent result from the Beretta where they show that this formula is valid on polygons too. Okay, but still is more regular than this result where omega was only open. Okay. Okay, so now I'm going to show numerical results for the EIT, where I use the distributed shape derivative. I'm just going very quickly to explain the numerical method that we use. We use the level set method, which is an implicit representation of the moving shape. So you have the set omega t, is parameterized by the time t. Is going to be all the points such that some function phi at time t is negative. Okay, so it's an implicit representation, because the boundary of omega t is the set of points where the function phi is equal to 0. And the dependence on the domain on t depends on the dependence of phi on t. And why this is useful is because you can have easily some change of topology of the domain. If you do an explicit representation of the boundary, it's difficult to change the topology. But with the implicit representation, it's very easy. For instance, here you have an example. This red function would be the function phi. And if you move this function up or down, you can see you will have a change of topology in the level set. The level set, it corresponds to the set where you cut with this blue plane here. Just the function going down, and you see the gray region changes the topology. Okay. So the relation between the domain evolution, which is determined by the velocity v, and the level set function, is just a transport equation. You just need to write what it means for a point x of t to be on the boundary, and differentiate with respect to t, and you get a transport equation. And then you need a velocity v. You need a vector v, which is a descent direction in your optimization. And then you can solve the transport equation, and in this way you can update the level set function phi. So to get a descent direction, we solve this problem. And this is where the distributed shape derivative enters the optimization. So here basically is like an elliptic equation for v, and the x is the test function. And here you have minus the derivative, so it's easy to see that when xi is equal to v, then this one is going to be positive, so the shape derivative is going to be negative, and you will get a descent direction. And here, this dj of omega of psi, I can just use the expression that I computed for the distributed shape derivative. So I'm going to use this expression for the distributed shape derivative. And I could also use this expression, the boundary expression. So I have the choice between using one of the two. But this one would not be very practical because I would have to, instead of this volume integral, I would have to compute the boundary integral. And then there's the question of the accuracy. It was shown that using this volumetric expression, the accuracy is better. Okay. Okay, so then I'm showing you the numerical results for the EIT. So first, I'm going to start with some old, I mean, not so old, but results from the previous paper, which is from 2015. So you have three applied currents on the boundary, and you have full boundary measurements. Okay, and it gives an idea of what is possible in the reconstruction for this problem. So this first here image would be the initialization. By the way, you seeing the mouse? I'm not sure about this. Yes? Okay.
Yes, it's possible. Yes.
Yeah. So the first one here, the dashed line is the exact solution, the ground truth, and the red line is the initialization. So you cannot start too far from the solution because these problems, they have a lot of local minimizers. So if you start too far from the solution, it's difficult to get a good reconstruction. You can get stuck in a local minimum. So this raises the question of the initialization, of course, but this is like yet another topic of inverse problems, how to get a good initialization. So here I will just assume I have a reasonably good initialization. This is an example of reconstruction if you don't have noise in the data. So even if you don't have any noise in the data, it's not possible to get the exact solution. But it's quite close to the exact solution. So in fact, it's a really good reconstruction for EIT. But a reconstruction without noise in the data, it's called inverse crime, if you are not familiar with inverse problems, which means it's a completely unrealistic case because in inverse problem, you always have noise in the data, right? But it already gives you an idea of the best case scenario. What is the limit of what you can reconstruct? Okay, and then I increase the noise. So this one is with 0.43% noise. Then you have here is written here 1.44, 2.83, and 7% noise. So you can see until this 2.83 noise, you get a reasonable reconstruction. With 7% noise is really quite degraded. You still get some notion of the position, but the shape is really wrong. But it's quite a lot of noise. Yeah? And also you don't have so many currents. You only have 3 currents. So if you want comparison, these kind of problems of EIT, you can show that you can reconstruct exactly the solution, theoretically, if you have an infinite amount of measurements. So, but in practice, you have much less, obviously. So you only have a few measurements. So the question is, what is the best reconstruction you can get with only 1 current or only 3 currents? Okay, so we try to have as little currents as possible to test the algorithms. But you can see here in this example, which is also from this paper from 2015, if the shape when the shape gets more complicated, it's more difficult to do the reconstruction. So here I had to put more currents to get a reasonable reconstruction. So now I have 7 different currents. So the currents, they correspond to this function GI that I showed in the beginning, okay? But still, with 7 currents, you can get a reasonable reconstruction with a bit of noise in the data. Now I'm showing results for this recent paper with point measurements. So if you remember the figure from the beginning, the red region is where we do the, when we apply the currents and where we do the measurements. So these points, these black dots, they represent the locations of the measurements, okay? And so that means we have very few measurements here, just a few measurements at these points. And we try to reconstruct this concave shape. So this would be the ground truth. The initialization is this red circle, and the reconstruction is this one. So it's actually a reasonably good reconstruction, because the concave part usually is very difficult to reconstruct because it's kind of hidden for the measurements. So, and there's a bit of noise in the data, and we use only 3 currents. And here there's a comparison between 3 levels of point measurements. So here you only have 16 points, here you have 34 points, and here you have 70 points. And you can see you start to have a quite dense network of points here. But it was interesting to observe that the reconstruction is still quite good with very few points. So you don't need so many points to have a good reconstruction. Here I computed the relative error. You can see is of the same order. Still, I mean, with more points, you get a better reconstruction. But in fact, the amount of points is more important for the robustness with respect to noise. So if you increase the noise, this case with only 16 points is going to get much worse. That is the main observation. So here you have some other examples with 70 points. This is the ground truth, the initialization, and you get a reasonable reconstruction. Now you have 7 currents. And here in this picture, I show the comparison with the full boundary measurements and the 70 points measurement. So you can see the reconstruction is quite similar, but when you increase the noise and you only have point measurements, then you really have a degradation of the reconstruction. Here you had 1.55% noise, and the result was much better than in this case. So the number of point measurements is not so important if you don't have so much noise. But if you have more noise, then you become much more sensitive to if you have less measurement points. So here you have more tests, so it's more or less so it's similar to what I shown before. The number of points does not really influence the reconstruction if there's not too much noise. This is a more difficult case because you have 3 inclusions. And that's it for the EIT part. So maybe, I don't know what time is it now. It's 2.
12.
So how much time is it normally?
45, 1 hour, just so you can take like 5 more minutes maybe.
Okay, so then I will just go quickly on the last part. I will just show the numerical results. Let me just go full screen again. Okay, so the other problem that I wanted to show is the seismic imaging. So the idea is that it's a similar inverse problem, but with the wave equation, if you want. So the idea is to produce images of the subsurface of the Earth by sending some wave that you create with some artificial sources on the surface, for instance, this vibrator truck. And then you have some points where you do the measurements. So this would be these receivers, usually called geophones in this setting. So there's a lot of similarity with the EIT problem. You have this truck would be just like the applied currents in EIT, and you have some point measurements at these geophones, okay? And here really the point measurements, they really make sense because it's a large scale problem usually. So you can only do the measurements of the reflected waves in a small geographic regions. It's just one device in a huge region. So there's a lot of interesting application for imaging the lithospheres, the glaciers, volcanic area, and in particular for hydrocarbon exploration is one of the main application and quite important here in Brazil. So, and the sharp interface approach, which is really my main topic of research, is quite appropriate for this problem because you have one case which is really interesting is the case of salt bodies. You have a body of salt, is this red region. You can really see a sharp interface between the salt body and the sediment. So here the values, they represent the velocity of the wave inside the subsurface of the Earth. So in the salt body, you have the speed is much faster. The wave goes much faster than in the sediment. And there's really a sharp contrast. So it's really interesting to put the sharp interface as a restriction of the optimization problem. Because this kind of problems, usually it's common to use a Tikhonov regularization, which really gives a smooth solution. So you can, in the region of these interfaces, maybe you're going to have a very sharp gradient, but not really a jump in the velocity. So the idea is that we worked on this, but really putting the sharp interface as a restriction of the problem, of the optimization problem. So we transform this as a shape optimization problem in the same way that we did for the EIT problem. And this has some advantage because it gives more information to the problem because you already know that the solution had this kind of structure. And this has a regularization effect because this reduces the impulseness of the problem. And another advantage is the sparse representation that I didn't use so much yet, but it could be used for this large scale problem. Okay, so let me pass this quickly. I will just, so the idea is that the geometrical setting, we put some is like this. You do measurement just on this, on this region, which is like the top, the surface of the Earth. And you have some inclusion, which are the salt bodies. And in a region close to the boundary gamma, you define some damping because you don't want reflection on this boundary gamma because it's like an artificial boundary, okay? Because normally the domain is unbounded because it represents the Earth. So, but numerically you need to work with a bounded domain. So you put some damping to damp the waves to simulate basically an unbounded domain. So then you model the waves with the acoustic wave equation. You can also do with the elastic wave equation. Then we computed the shape derivative. So it's also the distributed shape derivative, okay? And it's also this kind of least square problem with the pointwise also evaluation. So there's a lot of similarity with the EIT problem. The shape derivative has this structure, but now these S1 and S0, they are integrals over time. In the EIT, there's no time involved, so it was just a function of X. But here, it's an integral over time, so but the S1 depends on the position X. Then you compute you have the state, and the adjoint state is a backwards wave equation. And this is usual for this kind of, for parabolic or for hyperbolic problem. In PD constraint optimization, the adjoint equation is reversed in time, backward in time. The algorithm is similar as EIT. So I'm going to finish with the numerical results. So it's interesting to compare with the EIT because you get a much better resolution for this problem. The EIT has a low resolution, but this kind of problem, you can get a much more precise reconstruction. So here you only have data on the top here, on this part, okay? That's why the reconstruction is better on top and is more difficult to reconstruct at the bottom because there's less information that comes back at the surface. So here we use 10 sources, is like 5 Hertz dominant frequency. And we have 80 receivers only located at the top here. And then we get a good reconstruction here with a bit of noise. Here's some other examples with 2 inclusions. It's always the same. You can reconstruct quite well on top, but at the bottom is more difficult. You have this concept, there's a concept of illumination, and that there's a region started from which looks like this, where you can reconstruct stuff, but below this illumination region, it's impossible or very difficult to reconstruct because the waves, they don't come back, so you don't have any information. And here, okay, we tried many different tests. So here I'm just showing a few interesting ones. Here with 3 inclusions, we initialize with 3 objects here, and it's always the same problem. You have a problem with the reconstruction here. So usually people work with a very thin domain. I mean, this axis represents the depth. So it's like a Z axis. Okay, then I'm going to finish. Yeah, this is an example why you need to put the damping on the boundary. This is just a comparison, because if you don't put the damping, you get a very good reconstruction, but it's not realistic. Okay, because the waves, they come back from the bottom or from the side, and you get more information. But in the real data, you don't have this kind of information. Okay, so the conclusion is that we have this first work on FWI, but it's a very complicated problem because it's a large scale problem. So we still doing many developments at the moment. We need to automatize the initialization, increase the mesh size, the number of sources. We're working on piecewise smooth reconstruction instead of piecewise constants. We want to optimize the velocity of the sediment. And we're working also, what I've showed for FWI is with finite difference, because this is the state of the art, is the standard way of working on these problems. But now we are working with finite elements, which is quite interesting to get a good fine meshes close to the interface and have a better representation of the interface. And there's not so much development with the finite elements WI. And we also work multi-phase, where you don't have just 2 phases, but you can have more phases. Okay, so thanks for your attention. I hope I didn't pass too much the limit.
So thank you, Antoine, for this very interesting talk. So it's time for questions, comments. I have one, Antoine, regarding the numerical approach. You have this for the. I'm not sure. Can we see, because you have this bilinear form in order to get the descent direction, right?
So sorry, can you say again?
In order to get the descent direction, you solve this problem with this bilinear form, right?
Yes.
This bilinear form is like some kind of approximation of the some operator. I'm not sure, because, for instance, when you deal with the Laplacian problem, for instance, the classic, you have this bilinear form as a kind of an variational approximation of the Laplacian or something like that, and then you get the direction. So here you use this bilinear form for some.
It's just because it's a simple is a very simple one. But in fact, you really have the choice here. There's many possibilities to compute the descent direction and to choose the bilinear form.
Okay.
It's just it's completely arbitrary. This is more heuristic why we choose this one. It gives good results, but in fact, it's a research topic, like which bilinear form would be the more efficient. There's just one paper from Kevin Sturm on this topic.
Okay.
Instead of using the bilinear form, he uses convolution
Ah,
via the theory of reproducing kernel Hilbert space. So it's a kind of convolution to get a descent direction. And there's many, depending on the kernel that you get very different behaviors of the descent direction theta.
okay.
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 So you can get some more rigid displacement or more or less rigid displacement of the shape, for instance.
Okay.
And here is the same. I mean, you could choose a bi-Laplacian, for instance,
Yeah, exactly. Yeah.
and you would get a slightly different theta. You can even take a curl operator, for instance. You
Usually,
only need that it's positive to
yeah.
get a different
It-
direction. So you have a lot of options. Even here, we is not clear how to choose the alpha one and the alpha two, and because the alpha one is going to regularize the theta, and the alpha two is going to if the alpha two is large and the alpha one is small, or let's say when the alpha one goes to zero and the alpha two is equal to one, for instance, then your theta converges to the let's say the original shape derivative. So it becomes more and more sharp close to the interface.
okay.
And but if you exaggerate and take a too small alpha one, then you will get quite irregular theta in the numerical algorithm.
Okay.
So you have to find the alpha one, which gives a good, not too smooth, but which smooth is a bit. Alpha one should be sufficiently large. I don't remember the value we take in the numerics, but this is very heuristic. We just find a reasonable value, like 10 minus 2, and it works well for all problems so far.
Okay. Cool.
Uh,
Understand.
but it's heuristic. I mean, to say something more precise about this linear form or this coefficient is a bit difficult. It's going to depend on the problem and what can you really prove about this kind of stuff. I mean, it's not even clear what one would like to prove.
Um, some other question, which is more a curiosity. Is it possible to use this, or how related can be this to these imaging problems, like I don't know, for this segmentation, for instance, in which you look for get the specific shape of an organ or something like that in the medical imaging. Is it possible to do something like that? Is related or no exactly?
Yes, in fact, we have a paper with Intermuller. Now it's a bit older, the paper, but we do segmentation with this kind of approach, except that I think we use the boundary expression because the paper is older, is like from 2008, I think, the paper, 2010, I don't remember. So at that time, I did not even know about this possibility of working with the distributed derivative. But this segmentation, I think you could do the same approach that we did with this distributed shape derivative, and maybe it would work better or it would be easier to implement. But anyway, segmentation is a bit easier because you don't have PDEs, at least in the approach that we used. Maybe there's some more sophisticated approach where you can have PDEs too. I mean, if you do a really Mumford Shaw, you get a PDE because you have the gradient of the image.
Okay.
So yeah, in principle, it works for segmentation too. But I mean, for segmentation, there's already so many super efficient algorithm that I don't think it would be. I don't think it's really worth doing this for segmentation.
So we have some more questions or comments.
I just have a curiosity. Okay, I was wondering just if is it possible numerically to treat this the problem with a parallelization or some another numerical strategy like multigrid or something like that? Have you tried it, or is it possible or no?
In fact, this FWI, the parallelization is going to be very important. We didn't do it yet because we are more like beginners on this topic, but people work on this FWI problem. Usually you need, if you consider a bigger problem, you need parallelization, but this is more for the wave equation, not really for the shape optimization part. But you can also because for instance they look at 3D problems, solve the wave equation on a 3D problem, and you have it's not just one wave equation, it's like 1,000 wave equation in the 3D domain. And because for each they call it shots, for each shot is like one source. If I show you the equation like this F here, imagine you have 1,000 different F in 3D. Each F corresponds to one experiment, if you want. So you need to solve many wave equations on a large domain, and you need to parallelize. You need to parallelize with respect to the sources F and also with respect to the geometry. And for the for the optimization part, you can also parallelize. I cannot talk too much about the parallelization because I'm starting to work on this now and I'm really new to it. So I just know more or less what we need to do, but I never really started to implement. But you could, for instance, this PDE, okay, this you can parallelize. There's no, because it's just elliptic PDE. What else? And also the level set equation, I think you can parallelize to is like a transport equation or Hamilton-Jacobi equation. I don't know much this topic, but I know you can do it. But this optimization part of the problem is not so critical in the FWI. What is more critical is the PDE. Solving a lot of PDE and a lot of adjoint states. This is very expensive. And then once you have this data, solving the optimization problem is much cheaper, in fact. And what is expensive also is to compute, for instance, this kind of quantity, the gradients, the derivatives. So there's a lot of strategies to reduce the costs, reduce the memory. But we did not enter really these issues yet because we have considered small problems now, but we are just starting now to consider bigger problems. Okay. I don't know if this was your question, in fact.
No, yeah. Thank you for the answer.
But yeah, parallelization is really important for, and even EIT, you can parallelize what is easy to do is to parallelize with respect to this GI and the sources, because you just how do you call this? It's I forgot the name. It's like a trivial parallelization because you just solve one PDE on each node for each source. So it's very easy to parallelize. But in FWI, they do both. They parallelize the shots, the sources, and the domain. But then it's not so easy.
Okay. Do we have more questions, comments? Okay, if it's not the case, thank you again, Antoine. It was a big pleasure to have you here. Unfortunately, we could meet September. Fortunately, I think it's going to be possible. Finger crossed. And okay, thank you again. Thank you, thank you.
You're welcome. No, it was really nice. So I hope I can go to Quito in September or maybe later. Discover Ecuador, and let's see. I think the situation is getting better, but maybe it will take a bit of time.
Yes,
But
for
your
sure.
university is closed, even for research. You can't go.
Well, not that much. Actually, some labs are now open, I think. Then there are some researchers which are already going to the
Mhm.
university. But for classes and for big meetings, of course, it's still
Okay.
closed. But depending on the vaccines, I hope that things are going to be normal for September. At least it's what we hope.
And
So
the online lecture is okay. It's not too difficult.
I mean, it's like this is a new situation, but so far I think most of the professors
Uh,
are now, how to say, okay.
I think
It's
the most difficult is the exams or the exams.
comfort. Yeah, I mean, you have to put some 3 or 4 cameras on the students, or an open book test. I think is better.
What I do is I do randomized proof. Like every student gets a different one, but it's a lot of work.
Yeah, more or less like that. I am also working in this not connected test, let's say, but sending something which is kind of difficult, so they need to research a little bit,
Yeah.
or something like that. But because it's very difficult to test in these situations. But let's see.
Okay. Okay, then. Thanks for inviting, and see you
You're very
soon. Then.
welcome. Thank you for accepting the invitation, Antoine.
Welcome. See you then.
Yo, ok, gracias, colegas. Gracias por su
Gracias.
participación. Nos vemos la próxima semana. Thank you again, Antoine, and please be healthy.
Até a próxima. Podemos.
Hasta la próxima.
Eu não falo espanhol, mas eu entendo um pouco. Tchau.
Buenas
Até mais.
Thank you.